All right, part two. Compound interest. So I want to start out just to try to make sure you understand where a formula comes from instead of just saying, oh, here's a formula. So what I'd like us to do is remember what simple interest is and compare it with compound interest. Simple interest is going to be a situation where you calculate it by doing the principal times the rate times the time. And this is your money amount, this is your percentage, and this is the time in years. And of course that time could be different, but we're not going to worry about that. We're just going to always do it in terms of years for what I want to show you. So you've seen that formula. So if I give you an example so we can compare it. Okay, let's suppose the principal is $1,000. The rate is 10%. The time is for 3 years. And the interest that you earn is going to be 1,000 times, and you have to convert percent to its decimal equivalent. So 10% is 10 per 100, and 10 divided by 100 is 0.10. So that's where this decimal comes, or some of you know, you just move it 2 places to the right if that's what you want to do. So the interest, when you calculate, is going to work out to be $300. So the new balance, or the accumulated amount, okay, that word is amount, is going to be calculated by taking your principal. That's the letter they use, I guess. The letter A comes from the accumulated amount. Principal plus interest. So the new balance is going to be 1,000 plus 300, or $1,300. So if you're earning simple interest, that's how much money you get. If you're paying simple interest, that's what you'd have to pay. Now, I want to compare that with a table. And when I was learning statistics or even teaching statistics, then I always want to try to figure out what the formula means by doing a spreadsheet or some other longer calculation. And once I understand what it means, then I can go ahead and use the formula without any concern about not understanding what the formula is about. So here's what we're going to do. We're going to do the same amount of money. $1,000 is going to be 10% compounded yearly, and the time is going to be 3 years again. And so what I'm going to do is set up a table. And so this is year number 1, year number 2, year number 3. And we're going to calculate the interest by doing simple interest. We're going to calculate the new balance by adding those and show you what happens when you compound interest each year. So the first part of this is going to be no different than what you've ever done before. In other words, you're going to have 1,000 times 10%. And how long does year number 1 last? Don't tell me 3. Year number 1 lasts 1 year. So you're going to get $100. And so your new balance, I wish I had a little bit more room, is going to be 1,000 plus 100, or $1,100. So I'm going to get more room by just making my table go further down. So in year number 2 now, what you do for your principal is you use the new balance. And you're going to earn 10%. And how long does year number 2 last? It lasts for 1 year. So the interest you get is $110, and the new balance when you take $1,100 plus $110 is going to be $1,210. And when you get to year number 3 and you calculate the interest, you're now going to use $1,210, and then you do 10%. How long does year number 3 last? Well, each year lasts 1 year. And then when you figure out your new balance, it's going to be the $1,210. Oh, I forgot to write what this is. This is $121. So the new balance is going to be $1,331. So if you compare that for compound interest with simple interest, that's quite different, isn't it? It's $31 difference. Well, where in the heck did the $31 come from? Well, if you think about it, I remember my mother telling me back when I had to do a savings account that you're earning interest on your interest. So after the first year, you're earning interest on the $1,000 and the $100, and that's going to give you the extra $10. And then in year number 3, you're going to earn interest on the $1,000 plus the extra $21, or $210, I should say, and that's going to give you an extra $121. So you end up with this new amount right here that's going to be $31 difference by the time you calculate it. So again, what's happening here is a situation where you're going to earn more money or have to pay more money. Now let's do an example with a formula so I can show you the formula. Alright, so the formula that you're going to see is A is equal to P times 1 plus R over N to the NT power. And so what you need to realize is that the formula or the variables are all the same that you've already seen. A is the new balance, P is the principal, R is the percentage or the rate, and T is the time. But you have a new variable, and that is N. And N is referring to the number of times the principal is compounded each year. So there's going to be certain things that you need to remember. If they say compounded annually, then it's 1 times a year. And by the way, I'll give you this formula. I'm just not going to give you this information over here. Semi-annually, you should know that that's 2 times a year. Quarterly is 4 times a year. Monthly is going to be 12 times a year. And then daily, well, we're going to use something called the banker's rule. And the banks basically treat every month the same, whether it's February or this, excuse me, this April that's lasting forever. But they treat everyone as if they're the same, and they have 30 days. So 12 months times 30 days, they use 360. And that's what your book uses for daily, is 360. Now, the last time I taught business calc, they used 365, which is more normal, what everybody would have guessed if I asked you how many days in a year. So this information on the right-hand side, that would need to be known, and then this formula would be given to you. So let's go back and do that example that we just did the long way and see if the formula will work. And so you have 1,000 times 10%. I'm doing the wrong thing, excuse me. I have 1,000 times 1 plus 10%. And compounded annually is 1 time a year. And so we'd have 1 times 3. And so your new balance, this should be new balance, by order of operations, you'd have 1,000, and it's 1.1 to the third power. Now, if you have a calculator like the ones you borrow, that TI-30II, I forgot the number anymore, SX or something, then you can pretty much type it as you see it. But if you have a cheaper calculator, but like the ones I have at home, this is what you'd have to type. You'd have to hit a button looks like this, put the 3 in there, hit equals, multiply by 1,000, and then hit equals, and your answer would be the answer that I expect it to be, the $1,331. So again, you can either type it in as you see it right here, or you have to go through order of operations. So anyway, it depends on your calculator. So you see the formula works, but you can see back with the table how you calculate that. Okay, so again, I left one slide here, so I need to go ahead and erase this. So I'm going to count to 3 and then erase it. Alright, so it's going away. And again, I'm going to go ahead and write the formula for us, but I'd like to go ahead and do another problem. I'm going to have to get my calculator out because I don't have this done ahead of time. So let's, for the fun of it, say we got lots of money, $240,000. Might as well pretend we've got lots. We're going to earn 8% compounded monthly. And let's do this for 5 years. And so when you calculate this according to the formula, you'll have 240,000, 1 plus 0.08, compounded monthly means 12 times a year, and that's going to be raised to the 12 times 5 power, 5th power. Okay, so you don't have to wait for me to type everything. I'll do that in just a second, but this is the process I'm going to do. If you have a good calculator, a calculator like you can borrow if you're in the classroom, then you could pretty much type it as you see it, except you'd have a fraction, a slash here, so it'd be like 0.08/12, and then you probably have to have a caret symbol and then a parenthesis, something like that. And I don't think you need a multiplication symbol for that situation. So that's if you have the calculator like in the classroom. If you have the other calculator, you're going to have to do it by order of operations. So this is what I'm about to do on my old calculator so that you can see the process in case you're stuck with an old calculator as well. And honestly, I just multiply the 12 times 5 in my head, so that's where the 60 comes from. So the next step then would be to multiply by the 240,000. I'm going to pause it so I can do it. So the number I get, $357,562. And when I round to the nearest cent, it's going to be 97 cents. So if you compare that, if you take A minus P, that gives you the interest earned. And so if I was to subtract 240,000 from that, which I'm just going to do on my calculator, I'm going to end up with the interest is $117,562.97. So quite a bit of money, and that's what happens with compound interest. Now, what I'd like to ask you about is if we were to compound it 360 times or daily, would we get an astronomical more amount of money? And the answer is no, we wouldn't. Okay, if I was in class, I'd make you take a vote to see who'd make a fool out of themselves. In all fun, I wouldn't really pick on you too badly, to see who would be accurate and who wouldn't be accurate. So in just a second, I'm going to go ahead and type in what happens if we do it daily. And I'm going to leave all of this information on here, and I'm just going to do it on the calculator. So that means 360 days. And so if I change the color so I can kind of keep track, my new balance, when I use my formula, it's going to look like this now. So I'm going to type it on my calculator and pause this so you don't have to wait for me. So what happens then, if you compare the two amounts, you end up with an extra $459.05. I would take it in a heartbeat, but it was not astronomical like some of you may have predicted if I'd have put you on the spot in class. So what happens? Well, I can tell you what happens is, yes, you're doing a higher power, but you're doing a smaller number right here. So basically, then the compounding interest, the more times you do it, it starts to level off. It starts to reach sort of a plateau. And so you don't get significantly larger amounts of money. You'll just get a little bit higher, and it will keep growing past this, but it goes very, very slowly. So what I'd like to do now then is talk to you about what would happen if we talked about compounding it an infinite number of times. And the idea is to do compounding continuously. So let me see if the slide next, yes, there it is. So let me make sure you can see that. Let's suppose that we are standing on a street that has an infinite number of banks on it. So just pretend. So the first bank compounds the interest one time a year. The second bank does it 2, the third bank does it 3, the 50th does it 50 times, the millionth bank does it 1,000,000 times. And let's do this calculation where we just have just $1 for our principal. The rate of interest is 100%, which we know is the same thing as 1.00. And the n is the thing that varies. Okay, so it depends on how far down we go. And the time is going to be for 1 year. So if you plug that into your formula, you would have 1 times 1 plus 1.0 divided by n raised to the n times 1 power, which is basically the same thing as 1 plus 1 over n raised to the nth power. Now, I normally don't let you see all the numbers, but I have this handout or this sheet that I show on the screen on the overhead, and I wish I could cover part of it up, but I can't. So it's on the next page. So let me move to the next page. And you can see then, if I was to use the overhead or the Elmo to show this, that if you go to bank number 1, you're going to double your money. So let's keep going. Go to bank number 2, you're going to have an extra 25 cents. In other words, you're going to gain an extra 25% on your investment. So if I go to the third bank, I'm going to have 237, some extra left over. So I'm going to get an extra 12 cents or an extra 12%. So I'm going to keep walking for a while. So if I go to the 10th bank and I calculate that, I'm going to have $2.59 with some money left over. So if I go 90 more banks and I go to the 100th bank, I'm going to have $2.70. So that's an extra, what is that, 11 cents? So 11%, you can't sneeze at 11%. Okay, and if you go an extra 900 banks, well, look at the whopping amount that we get out of there. We get an extra almost 1.7 cents. So I don't know about you, I'm tired of walking. I don't know how far I want to go. So what I'm going to do is not going to walk, we're going to do it mathematically. So if I go 9,000 more banks, I'm going to get an extra 0.2 of a cent. And if I go 100,000 banks, which is an extra 90,000 banks, I get an extra fraction of a, what in the heck is that? That's the 4th decimal place. So I think that's an extra 1/10,000th of a cent. Well, if you keep going, there's the 1,000,000th bank, and you get an extra fraction of a penny somewhere, like right about here, versus here. And so definitely, what happens? Now, I'm going to swear to you on a stack of math books and calculus books, if you take my calculus class someday, I will show you where this number comes from. But this is a number like pi. Remember pi? Pi, if we're in our room, there's a poster that you all never look at. It is a decimal number that goes on forever. It's an irrational number. We talked about that the first day of class. So e is another number that's an irrational number, like pi, as it goes on forever, where it doesn't repeat and there's no pattern to the digits, and it's going to be what is basically a number that is irrational, that cannot be expressed as a ratio of integers. Well, where did they get the letter E to use for the number E? Well, they decided to name it after this guy. His name is Leonhard Euler. I forget how to spell it. I think it's this way. And so he does a lot of the symbols that we've used all through our algebra and math careers. Some of them so pretty decent, but then you're going to hear about one that I hate later when we talk about section 3, or is it section 2 of this chapter. But anyway, we need to go ahead and remember this number, because this number occurs in nature in a lot of different places. It's going to occur in population growth, money growth, cell growth, cell decay, radioactive decay. Anything that occurs in nature, this number E happens as well. So I just wanted to show you where this comes from and talk about it this way. So what does that mean as far as your formula for compounding interest? Let me write it down now. Let me check to see if I didn't go to the next one. Nope. Okay. So I just have blank slides from here on out. If you want to compound continuously, and that means n is equal to infinity, then the formula you have is A is equal to P times e to the RT power. I jokingly call it the shampoo formula because of the shampoo pert. Some of you may not know it. Some people look at me like I'm crazy, but oh, it's okay to be crazy every now and then, especially with what's going on these days. So it's the principal times e to the RT power, and you're going to ask yourself, well, where do I get this number e? I don't want to have to type that 2.81827, whatever the number is. I don't want to type it in all the time. Well, on your calculators, you're going to look for something that is the ln button that you're going to learn about later in this chapter. And right above that, you're going to see the e to the x on the plate part of the calculator. So depending on your calculator, you're going to have to either hit second or inverse to get this part of the calculator right here. So find your scientific calculator. You need it for the material and the things we're doing right now in Chapter 4. Honestly, you didn't need a scientific calculator until now in this particular chapter. So if I wanted to do that same problem we talked about earlier of $240,000, and it's going to earn 10%, no, 8% was what it was, compounded continuously. For 5 years. Well, if you learned your lesson, this is not going to be astronomically larger than that last number that we calculated, which I don't have it on my calculator. I thought I did, but I don't. So let's go ahead and do this. We have 240,000 e raised to the 0.08 times 5 power. And again, if you have a calculator like the one that's in our classroom, then when you hit that button, it's going to give you that automatically. It's going to hit, if you hit the second or inverse and then e to the x, it's going to give you what you see right here automatically. What you have to then do is type in the rest of it. And so you type in the 0.08, the multiplication symbol, the asterisk, whatever that turns out to be, or just a multiplication symbol, 5, and close that, and hit the enter, and it will give you the answer. If you have the old-fashioned calculator, because who knows what you're stuck with, you need to do 0.08 times 5, hit the equals, and then you hit that second or shift. Oh yeah, that's another version, is shift. I forgot that one. That will do the same thing as those things. So you hit that, you hit the ln button. It's not really the ln button. You're hitting the e to the x because you did that second or shift or inverse. And then you type in nothing. actually. It will do it for you automatically, and so you're ready to do the rest of it, which is to hit multiplication 240,000, and I think I have to hit equals to get what the answer is. So I'm going to pause it while I do that. Alright, so I saved you some time watching me bounce back and forth to get all the numbers that we did earlier. And so if we look at everything, the first calculation we did, this is the amount that we ended up with. And we did it monthly, 12 times a year. We did it daily, and we got an extra $400 some if you remember. Now, if you do it an infinite number of times, n is equal to infinity, we get an extra $15.91. So I could take you to McDonald's or something, and we could both get some kind of meal, maybe more than Happy Meals. But anyway, so I'll take $15.91 if I can get it, and it's not going to be astronomical is what I wanted you to see. All right, we're finally almost done with section 4.1, but there's one more thing I've got to remind you of, and that's graphing. Okay, so I thought I had everything ready, but I know what I need to talk about, so here it is. If I was to ask you to graph e to the x, you have to ask yourself, e is approximately equal to 2.71828. So is that number bigger than 1? Yes, and if it's bigger than 1, what's the graph going to look like? It's going to look just like the 2 to the x, basically, as far as I'm concerned, with that same horizontal asymptote. So just for review purposes then, let's just pretend like we've got a g of x, and it's a negative e, and let's pretend like we've got an x minus a 1, and let's do minus, let's not get carried away, a 2. So I got minuses all over the place. So let's do this graph relatively nicely. Oh goodness, I keep missing. Okay, so we're going to graph this, and we're going to do it step by step like I've done before. So if I was to ask you to graph the e to the x, you know what that looks like. It looks like this. If I was to put a negative in front of that, then it doesn't look like this anymore because it rotates over, and so your graph is going to do something like this, and the horizontal asymptote stays the same. The next thing I would do would be the up and down shift. So I'd have the negative e to the x minus a 2, and that's going to cause our graph to go down 2 units, and I draw the horizontal asymptote first. Please don't forget that. It has saved so many people's you-know-whats that you need to remember that. And the shape is going to do something like this. So last but not least then, if I graph this, and let's graph it in a nice beautiful red, then I would graph for my answer on this graph, I would graph my horizontal asymptote, which is the equation y equals a negative 2. And this point that was right here before is now going to have to shift. Because of this, it's going to shift, if I solve that, to the right one. So I'm going to have this point, and my graph is going to do something like you see right here. Okay, so you should be able to graph them when you have e to some power and so forth. So this is what you need to be able to do from section 4.1. And 4.2 is going to be extremely important, but I'm going to do that video next week, next Friday. So anyway, we'll catch you later. Good luck on your test on Monday. I hope you do very, very well.